first of all, let me present guest of honor for this one, John Hughes, who's been a functional programming enthusiast for 30 years at universities of Oxford, Glasgow, and since '92 at Chalmers in Gothenburg in Sweden. He sat on Haskell design committees, is the author of over 100 papers with classics like Why Functional Programming Matters. He's the co-creator of Quickcheck in Haskell, founded Qvik, which now brings the most powerful of property-based testing to the Erlang ecosystem and the Beam virtual machine. He's been an ACM fellow since 2018. By comparison, I'm Fred Hebert. I wrote a book on property-based testing, so it's obvious I have as much credentials as John has to be hosting this. I will be facilitating today. If you are not aware of how this works, if you go into the Whova app or web page, there's a Q&A tab in there. There's also a chat tab, which I will be monitoring to bring up the questions for John and possibly myself. And otherwise, I'll be gladly asking a few questions I've prepared ahead of time to launch a discussion. John, is there anything you want to say first?
No, that's fine. Go ahead.
All right. So the first thing that might be interesting for this entire thing would be, how would you define or introduce property-based testing? I'm assuming that we have some people who know the practice, but we also have some people here who are only looking at it and not exactly sure of how this is working.
Yes, so the basic idea behind property-based testing is that instead of thinking of test cases, thinking of examples of things that your software should do, you try and think of general principles, general properties that should hold for all executions of your software. And then you write a test that basically generates random inputs to your software with control over the distribution. You run the software and you check that that general property holds as the result. And if it doesn't, then you found a bug, probably, either in your property or in the code. It can be in either place. And the next thing that property-based testing tools do is automatically minimize the test case so that you end up, we call this shrinking, you end up with a minimal example that provokes the bug, the inconsistency between the property and the code. And those are usually very easy to debug. And I think that, I really want to emphasize the importance of the shrinking step. If you just do random testing, and you run a random test on your code and it fails, then you, generally speaking, have some large input of which maybe 95% is irrelevant for the failure. That's not a good starting point for debugging. But when you bring shrinking into the picture so that you automatically minimize the test case, then you get something where everything in the test is relevant to the failure. And the difference between the situation you're in when you have to debug the problem, when you have a large input, 95% of which is irrelevant, and a small one that only contains relevant stuff, it's the difference between night and day.
Right. It's possibly one of the big differences with tools like fuzzing tools used by security specialists a whole lot, which is about, they do have that random aspect of generation and stuff like that, but it often lacks that reduction aspect of it and trying to tell you what exists properly. There's a bit of difference as well with the idea of what is a property, right? A lot of fuzzing is mostly, this doesn't crash when I put new random inputs. Property-based testing is a bit richer from that point of view.
Right, exactly. And that was really what appealed to me about the idea from the start, that, you know, I like to think about what are the properties of my code. If there are equations that the code should satisfy, you know, things like a very trivial example that I might often start a property-based testing talk with. It's reverse of reverse is the identity. Right, so that kind of simple example, you know they should be true, and I just like the idea of writing those properties down and then having them tested automatically.
And that's something that's sort of common in a lot of tutorials, right? The reverse of the reverse is kind of the canonical example we see in every single starting tutorial. And then you have the kind of usual suspects from that, right? If you're implementing a tree data structure, there's going to be preconditions and post conditions that are given in the paper, and then you can implement these. And there's usually a sort of limited scope to what you can do with these properties unless you're used yourself to writing papers and figuring these out. Then there's this entire aspect that came when you developed Quickcheck for Erlang, which is the fancier model testing and stateful approaches. Can you speak a bit to the difference that we have at this point there and how you go from one to the other, right? Because a lot of the early tutorials when somebody's starting is the basic stuff with the magical properties of the input and the output are reversible, but it's kind of super hard to graduate from one to the other. And I'm curious to see what you can say about that.
Yeah, that's right. So code without side effects is easier to test. I mean, that's just a God-given truth. So there's no getting away from that. And when you write down properties of code without side effects, pure functions, often equations are a good form. There can be other properties of that sort as well. But those are really easy to work with because you don't have to worry about the history of a test. You just look at the inputs and the outputs. So in order to test stateful systems, then you have to consider the history. And so we generalized the idea of properties to define libraries that would generate a sequence of API calls. And then you want to generate sensible sequences of API calls. And that means that you need to have a model of how each API call affects the state of the system, but you can have a very simple model of the state, just enough to enable you to tell whether a sequence is sensible or not. And then based on that model as well, you can predict how each API call should behave. So then you're running tests that say, for any randomly generated sequence of calls that make sense according to the model. So every operation has a precondition here too, but a precondition applies to, it depends on where it appears in the sequence. Then whatever you said, your postcondition should be, of all those calls, should also hold. So we came up with that actually when we started our company. Then we developed some Quickcheck tests for Ericsson, and it was a stateful system. And at that point, we had not developed this state machine formalism. And so we just had to do everything by Steam explicitly. My goodness, it was painful. And it was really after that experience that we realized that you can't necessarily just take a tool from a paper to a customer and expect it to work. So that's when we came up with this state machine stuff, which we've used in many variations ever since. And just recently, we have a new wrinkle on that, which we've come up with to help testing smart contracts. And here, if you think of the kind of tests I'm talking about, we're generating random sequences of API calls. You're kind of taking a random walk in a state space. And that's very good. You can check that nothing bad happens, which is one kind of property. But with smart contracts, it's all very well to check that nobody manages to steal your money. But there's another kind of property you want as well, which is that you can always get your money back again. That is, it doesn't remain locked forever in contracts on the blockchain. And that's a different kind of property, right? Because if you just take a random walk, it's very unlikely that you will actually get your money back, or you'll end in one of these goal states. And if a random walk doesn't reach a goal state, so what? It's not a problem. So what you want to be able to do is to say, no matter what random walk I take, no matter what state I get into, I can always get my money out. And reaching that goal state, that may require a strategy. So the new thing that we've added is a way of allowing users to specify, here is my strategy for getting my money out. And then we test that your strategy always works.
Because that's one of the questions that we've got from Jonathan Arnott in the Q&A right away, which is how can we ensure that the random sample of properties we have can catch bugs, right? There's a whole approach of dealing with the statistics and figuring out that you've got adequate coverage and stuff like that. And that turns out to be a much more important part of learning property-based testing than you think on the surface, because a lot of the marketing material is it explores the entire space for you, but there's a lot of guiding that needs to be done.
That's right. So, and this is really, really important and often missed by people who are just starting out with it. So I think it's important when you do property-based testing, you're generating tests and you don't see the test cases. So they're a little bit out of sight, out of mind. But just because you're generating tests doesn't mean you should throw your brain away. And if there's something you would worry about writing tests by hand, like have I covered all my code, for example, of course, you should measure and see, have I covered all my code with the property-based tests? And if not, you probably need to tweak the random distributions in order to reach those harder to reach parts more often. But it's not just a question of covering code. I always try and think, what is sensible to measure about the behavior of these tests? You know, like if you're looking at smart contracts, how much money remains in the smart contract at the end of the test? And then I might want a certain distribution of that. Or if there's a number of different places where it might end up, you know, how often does it end up in wallet A? How often does it end up in wallet B? How often does it end up in wallet C? Measure all of those things and make sure that the distribution looks reasonable. But then the other thing is, and this is something I always do, plant bugs. So whenever I'm writing code with properties, if ever I think, well, here's an obvious way to do it, but I don't think that should work, I'll write it the obvious way. And then I'll make sure that my properties can reveal that bug. And when you do that again and again and again, so what you're doing at this point is you're tuning the way you generate tests. And there is a lot of tuning involved in making property-based testing work well. One of two things happens. Either you find out that your tests do provoke the bug, or you tune it and then they can provoke the bug. Then that's good. You have more confidence in your tests. Or you can't provoke that bug, no matter what you do. And then that may very well be because it's not actually a bug. So this also happens. You know, I expect something to fail. I write the simple code and what do you know? It works. And that's a result too.
Yeah, in my experience, I do find that my properties are not good enough much more often than I find the code is surprisingly better than I expected it to be, though.
Well, yes. So, of course, it depends on how strict the properties you write are. You know, I like to write properties that a buggy implementation will not satisfy. But you could also, it depends how much time you have for writing properties, right? It's also worthwhile to write properties that just check simple things. And then when you write that, you know, they will miss them.
Do you find yourself like slowing iteratively with a small property that you make more and more and more complete so that you have like one larger test that covers a lot of stuff? Or you take the other approach, which is a lot of small properties that put together give you a certain confidence that all kinds of angles are being covered?
It depends what kind of code I'm testing. If I'm testing purely functional code, then I will normally have a large number of different small properties. But if you're testing a system with state, then you know, the way that we do that is we write a model, and then you write one model and you refine that model more and more and measure more things about it and adjust the distributions, etc., etc. But you're not going to make two models. So you end up integrating everything into the same test.
Does that test become at some point complex enough that it becomes unwieldy to maintain, do you find, or generally it's not that big of a deal?
Can be unwieldy, yes. So if you try and model the behavior of the system very, very closely, then the test becomes larger and more complex. And what we have noticed is that if you develop such a test and then you hand it over to somebody else to look after, and the system evolves, then people are not always very good at evolving the tests along with the system to make sure that they still pass. Actually, I did quite recently spend a bit of time updating the tests of parts of Quickcheck, in particular the parts that deal with simulating the abstract machine for doing parallel testing. And of course, the OTP virtual machine has evolved. And so I had quite a lot of fun modeling the changes in behavior, and indeed fixing one or two bugs that had crept in because the behavior changed and suddenly code that had worked didn't work any longer.
We do have a question right now, which is from Eric. I don't know if I'm pronouncing it right, but can you say more about checking the liveness properties with property-based testing, particularly in the Erlang Elixir ecosystem?
Oh, checking liveness properties. Well, so this thing that I was mentioning with the smart contracts, it's almost a kind of liveness property, right? I want to say that it's always true that you can reach a particular goal. But
this is sort of different from the liveness property that we see in formal specification tools like TLA Plus and stuff like that, though.
Right, yes. So liveness properties in general, the definition, I think, is that all counterexamples are infinite. And we can only find finite counterexamples with Quickcheck, so that they become a little bit more problematic. So what we tend to do is, for example, if you want to demonstrate that something always eventually happens, then we have to figure out a deadline. And then the property that we actually test is that, no matter what you've done beforehand, maybe we compute a deadline appropriate for this test case, then something should happen within this amount of time. So that's a cheat, really. But in that case, when you say that something eventually happens, you're saying there exists a time at which the thing will happen. And exists is difficult to test.
Right. We don't have this power of validating the completeness of the walk we're doing right now and saying, like, we actually covered all possibilities. Each of them is only partial.
Right. So if you want a counterexample to a property with an exists, and if the exists ranges over an infinite set, as most of them do, you need to run an infinite number of tests to demonstrate that it's really a counterexample. And we can't do that. But what we always do instead, and we've done this in many different contexts, is if you want to test that there exists something with a given property, we make the user tell us, all right, what value do you think that has? It might be a deadline in an eventually kind of property. It might be, this strategy for reaching a goal state that I was talking about. But whatever case, when there's an existential quantifier, that's always logically equivalent to a property with a Skolem function in. The Skolem function, logically, it's just the code that computes what value is going to satisfy that exists. So we put the problem in the hands of the user. We say, you tell us which value you think should satisfy this. And then we either say, okay, that worked in all the tests we ran, or no, it doesn't. And here's the counterexample. It's a pragmatic approach.
Yeah. Something that comes to me with, this question, the answer you gave to the previous one is that, there is non-negligible effect that comes from the experience and the expertise you have in writing these properties. And one of the questions that I know I've asked myself in the past is, if I were to bring this into a software team I work with who has no experience of that, it's not obvious how to bring the practice in, right? Something like test-driven development has a very, very small framework with non-fancy automation, and you can start small. How do you suggest that people bring in property-based testing as a practice within their teams? What are significant steps that you think could be done with that? Because I know your company has done training in a bunch of places as well for that kind of stuff.
Yeah, so some people find it easier to pick up than others. And I think one good strategy, if you've got a team of a little size, is to find the person or people who embrace these ideas most readily and let them become the specialists. Because it is a different way of thinking about your code and thinking about your testing. And so it's good for somebody to focus on that and really develop those intuitions. Of course, there are easy ways to start. Like if you could write unit tests, then usually there are some arbitrary values in there, so you can randomly generate them instead. But I don't, that is an easy way to start, but I don't like to encourage it all that much because it tends to lead towards, it doesn't really lead to getting the most out of property-based testing. So what I like to do is if I'm testing a system with, stateful system with an API, let's suppose it's got n operations in it. I'll start with just one operation. And I'll think, how much of the state do I have to model to be able to call this one operation and test it? And then you can work step by step. So you take the next operation, one operation at a time, and you have to enrich your model enough to manage, 2 or 3 operations maybe. And when you do that, then to begin with, all of the bugs you find are your own. So this is something that is useful to know if you're trying property-based testing for the first time, that of course, the property-based tests are the new code. So where are the bugs going to be? Usually the system has been running for a while and it's already been tested and the obvious bugs have already been found. So you're going to find a lot of bugs in your own code. And then after a while, I've done this from the documentation and I write a test that tests that the system behaves as the documentation says. And I find a bug and I report it to the developers and they say, oh yes, we must document that. Right, because documentation is never completely up to date. Right. But after a while, something very interesting happens. So once you've got, let's say, n operations modeled, and you add the n plus first, the amount of work you have to do when you're building the model, it's linear in the number of operations pretty much. Okay. If it requires you to enrich the model, it could be a little more than linear. But by and large, for every new operation, you do a constant amount of work. But if you think of the variety of tests that you can generate when you're generating sequences of operations, it's going up exponentially. And that tends to start to trigger bugs. Like they come out of the woodwork like water. That's a very mixed metaphor, isn't it? But there comes a point where the bugs just flow. And I've actually had people say, could you please stop testing for a while so we can fix the bugs you've already found? When you get to that point, it is so much fun, I can tell you.
So you do reach a kind of tipping point, and it's interesting to start from a solid core. I'm just, doing a synthesis of what you just said to make sure I got it properly. You start with a kind of solid core so that you know that the issues are with your tests at first. And once that solid core is tested and you start expanding, you reach that tipping point where you do find new behaviors and you have this kind of trust in the tests that you've started to build, where all of a sudden it becomes a great searchlight and guiding light in how you build your things to make sure they're solid enough.
That's right. Yeah.
Nice. We've got a question from Christopher Cote, if the name is to be pronounced in French. Any hints on exploring your property space for something like a network protocol state machine, or even something that specifically targets gen statum as a behavior?
Yeah. Well, so I would be using the state machine modeling framework for testing those kinds of state machines. The problem once you introduce networks is often that you get non-determinism in the tests that you're running. And so how do you take account of that in the model if there's more than one state you might move to? It's a little bit awkward. We've done, for example, we tested Dropbox, where there's a huge amount of non-determinism going on, because there's the Dropbox daemon, and who knows what that is doing behind the scenes. The test has to accept any valid behavior there. And what we did there was we modeled the set of all possible states that the system might be in. So our model said, we had a model of the state of the system. Our operations would change that state. But we also had a set of background operations that the Dropbox daemon might be doing. And so we just computed, if we take all combinations of background operations, what states might we end up in? And then we do another operation. And every time you make an observation, you can rule a bunch of states out. So that can explode in that you get far too many possible states. But with a bit of care, you can often control that. And when we were doing the Dropbox testing, then we found that sometimes, very rarely, the state space would really explode. But a lot of the time, there were less than 1,000 states. So we just said, okay, if we get more than 1,000 possible states, we'll say, oh, can't decide this test. Go on and do another one. And that was good enough to find a number of rather strange behaviors.
Right. I've heard of work that Christopher Michael John did as well, who a lot of people might know for the work he did with CRDTs, where he managed to do these simulations by adding to his state machine or stateful model events, like the network is getting disconnected right now, and then reconnecting it and maintaining the properties that, in his case, the same semantics remain whether there was a failure or not during the execution overall, and being able to test that by injecting these events as a sort of semi-deterministic part of the model he was building, which was a very interesting approach. Robert Carbone is asking, do you test networks with simulated annealing as a way to explore the state space there or something?
No, we have not done that. So we use really pretty much exclusively random search. And so we haven't looked at anything more complex of that sort. And random search has worked pretty well for us so far. So it is tuned random search. So I was saying there's a lot of tuning involved. So we've not used any more complicated search strategies.
That makes sense. Still, to me, in the spirit, and until we get another question, one of the things that I found a bit interesting in approaches like TDD and even mutation testing is this idea that they can have extensive and complete frameworks, but a lot of these practices are something you can adopt without any of the framework. And even the mutation testing, where you change the code and you try to see if you find bugs, is something that you do while coming up with properties. I'm kind of wondering if there's anything in your experience that you can take from property-based testing and bring back into regular testing without a framework, because property-based testing is generally very framework heavy as a way to do the search, to do the shrinking, to do the reduction of all this stuff. Is there stuff that you find that you use in property-based testing, and when you get back with regular testing, you import new practices or approaches that are beneficial without the benefit of the framework?
Do you know, I don't go back to regular testing. Why would I do that? Do you?
I do, because I sometimes program in languages that don't have the fancy frameworks.
Yes, if I program in a language without a property-based testing tool, I miss it very, very much. It's so easy to screw up.
Yeah, it brings this sense of confidence in a lot of what you write, that when you don't have it, you're not being as thorough as you could be for the same amount of effort involved.
Yeah, so I think I've done things like set things up so that I can run Quickcheck and talk to code in model language and test it that way. So of course doing random generation of test cases is something that is quite easy to do. All you need is a random generator. So if you're satisfied with just writing some properties and generating random inputs, then you don't need all that much in the way of tools. But in that case, when a test fails, you're going to have to simplify it yourself, because it's making the generation and the simplification work well together. That's what a lot of the tooling is doing for you. And I really think that I cannot emphasize the importance of shrinking enough. It really transforms the usefulness of the approach. I think you really want to be using a tool that does that.
It's something that I know I've seen happen with a bunch of people where, they have this big stateful model that is cumbersome and long to execute, and then it finds a fault, but shrinking at that point takes forever because the model itself is slow. How do you cope with that, right? The big benefit is having the minimal subset, but generating it can be so time consuming that it's almost as fast to just read the big thing and figuring out yourself sometimes.
Yeah.
What does that say to you?
So a good tool will let you turn shrinking on and off at different parts of your model. So for example, one of the things that can happen is that there's maybe an integer in there. And maybe the smallest value that it fails for is 2,331. And getting to that value exactly is going to take a lot of tests to pin it down precisely. But maybe the value of the integer just doesn't matter very much, or maybe you only care, within 100. In that case, shrinking is always customizable. So you could customize it to say, well, try multiples of 100, but don't try the numbers in between. So sometimes we turn shrinking off. For example, if we're testing something, an authentication protocol with passwords, shrinking the password is almost always uninteresting. And so we'll turn shrinking off for the things we don't care about, but make sure that we have shrinking for the things that we do care about. So that helps avoid these very, very long shrinking times. Something else, though, that happens is if your test is not deterministic. For example, if let's suppose there's some state that isn't reset at the beginning of every test, then what will happen is that the failure of one test will depend on the test you ran just before. The effect of that is that tests pass or fail essentially randomly. And when that happens, the shrinking search is at a loss, right? So normally what happens with shrinking is you very rapidly get down to a small test case, and then maybe you run another 100 tests even, just to get it down to exactly the minimal case. And that's fine. But if tests are passing or failing randomly, then what's going to happen is you just start off and it doesn't get very much smaller. And you try to change here and a change there and change there and all the rest of it. And it's just not going to work. So very often, the way to fix that slow shrinking is not to turn some of the shrinking off. It's to figure out why your test is non-deterministic. And what you can do is, in that case, is turn shrinking off altogether, run your tests until you find a counterexample, which will probably happen. That counterexample is no use to you, except that you can repeat the test. If you repeat it and it passes, now you know you've got a non-deterministic system. So the most important thing is to get that non-determinism under control. We had an example of this in some of the early testing we did for Ericsson, when we were testing a base station, radio base station, a 3G base station. You can tell how long ago this was. And the test was crashing the base station. And in that case, the only way to reset the state so we could run another test was to reboot the base station. And in those days, that took 2 minutes. So we were able to hit the bug fairly quickly, but we had a long sequence of API calls. And then we rebooted the base station at the start of every test. We went and we had a long lunch. And when we came back, we had a sequence of 2 calls that would crash that sucker every time. And it was a nice lunch.
Oh, it has
When
to
we
be.
came back, we had won. So slow drinking isn't necessarily a problem in itself,
Right.
if you get the right result.
Right. It's better than the excuse of, why are you not working? Well, I'm compiling now. It's still testing. So at the very least, like, it's active debugging. It's great.
Right.
We've got a little bit under 5 minutes. I think there's a decent segue in the last question we've got, or possibly last question we've got, which is there any Erlang or Elixir open source projects that showcase the power of property-based testing that you have in mind?
So one that we have been involved with quite a lot is REAC, which is not entirely dead. And there are quite a lot of property-based tests in there. So one could see a variety of different kinds of property-based tests, lots of these state machine model-based tests in the React source code. But the other thing that I would like to mention then is a very nice blog article by Andrew Thompson about testing Pool Boy. Have you seen that? So Pool Boy it's a worker pool process and a worker pool component.
Yeah, I think I remember seeing that.
Yeah, so you can check out workers and you can set the maximum number of workers, but you can also set an overflow so that if you reach the maximum, then it keeps a number of workers active all the time. But if you get to the maximum, it'll spawn a few more for you up to a certain limit. Anyway.
Yeah, I do recall seeing a lot of repositories by Jesper Lewis Anderson, J. Lewis, on his GitHub account do have a bunch of property tests with them. So I can recommend looking into these. They tend to be smaller libraries like circuit breakers and stuff like that, and playing with the properties. They're decently sized sample to get going. If you've never looked at stateful properties, however, looking into documentation or getting a bit of familiarity about how that model works is going to be helpful to figure these out.
Yes, that's a very good suggestion. Jesper Lewis Anderson gives wonderful talks about some of the testing that he's done.
Right. We've got a last question there that just came up, which is there a good library for making this easy to do with XUnit, which is Elixir's unit testing libraries? Really, right? It's kind of requiring its own framework. In my experience, like integrating property-based testing into an existing test framework is just you call the property-based testing framework from your unit test and see the result of something.
Yeah, that's what people tend to do with eUnit, certainly. I'm not sure it's really helpful in that it just gives you an extra layer of mechanism in between you and the test, as it were.
Yeah.
But,
it gives you sort of unified reporting, but in my experience as well, there's more richness to just working in the framework first step directly in there and doing what you can with it.
Yeah. So what I like to do is I like to work in the REPL. I like to run my tests in the REPL. I know maybe that's old-fashioned nowadays. I've seen many people struggling with all the files you have to change in order to make sure that your tests run when you do the build, which is no doubt a good idea. But if you just want to find a bug, I find working in the REPL a lot more effective for me. And certainly with our tool, then the interface that we have is designed for making it easy to use in the REPL and repeat tests and vary them a little bit and so on.
So yeah, for you, the interaction is one of the important parts. I think we've got about a minute left. John, do you have any closing words or parting words that you would give to the audience and participants that we had with us today?
Yes. So I know that many people find it difficult to come up with properties in the first place, and that is key to getting value out of property-based testing. And when I saw that, I wrote a paper called How to Specify It, which goes through, for pure code, 5 different ways of thinking that can help you come up with properties. So I just want to advertise that paper. I'm keen to get as many people as possible to read it and to get value from it. Because I think if those lessons were learned in the community, then they could make quite a big difference.